Okay, thank you, Bjorn. So good morning, everybody. Welcome to day 2. So the last thing we were talking about was this baby version of the trace formula. So now we are going to do the grown-up version. Okay, so this is theorem 4.2.7. in the notes. So let me just remind you of the setup. We have a hyperelliptic curve over FP. Of genus G. Okay, so there's our hyperelliptic curve. And we had this polynomial h, which is f to the p minus 1 over 2. So I want to define a matrix. This is the matrix we're going to take the trace of. So I'm going to define a matrix, which I'm going to call A sub f. So this is a G by G matrix. With entries in FP. And its entries are given very explicitly as follows. If I take the entry in the vth row and uth column, this is given by a certain coefficient of h. It's vp minus u, and this is for u and v between 1 and g. So probably a lot of you recognize this matrix. It's often called the Hassavit matrix of the curve, or the Cartier-Manin matrix of the curve. Really, when you call it these things, you should be thinking with respect to a certain basis for whatever cohomology space or space of differentials or whatever it is. I'm not really going to go into those cohomological interpretations. All I care about for this course is that the entries are given by certain coefficients of h. Okay, very nice concrete interpretation. So here's the theorem, is that if I look at the number of points on the curve over fp to the r, so not just fp anymore, now we're looking at extensions, this is congruent to 1 minus the trace of the rth power of this matrix. This is modulo p. Right, of course we can only get at modulo p because we're only looking at h modulo p. There's no higher power of p information here. In section 8 you'll find a generalization of this formula for higher powers of p. Okay, and this is for all r. All r greater than or equal to 1. Now, I don't think I'm going to go through the proof of this in the lectures. It's sort of worked out in the notes. There's some problems that help you work this out. I might just say a few words about it. The first thing you should notice is that when r equals 1, this really is just the baby trace formula, right? Because when r is 1, you're just taking the trace of AF, which means you're summing these guys over all v and u where they're equal, right? So v and u are both 1 and then both 2, and those are giving you the multiples of p minus 1. So that's exactly what you're getting in the baby trace formula. But the idea of the proof, I think this came up in the questions at the end of the last lecture, is that you first replace you know, we looked at f of alpha to the p minus 1 over 2. So you have to replace this by f alpha to the p to the r minus 1 over 2. Right? This expression is detecting if things are squares in fp. This is detecting if things are squares in fp to the r. Okay, when you do this, you end up with an analog of this polynomial, but with a much higher power of p. You get the p to the r here instead of p. So that's no good. But then there's some trickery which lets you express the coefficients of that polynomial in terms of the coefficients of this h. And it turns out, for magical reasons, that this is the relationship you get. Okay? There are a few different ways you can prove it. I've suggested one in the notes. Okay, so that's the idea. Let me just write down an example so we see what we're dealing with. So same example as before. Let's take p is 11, genus 2, and remember that the degree of h was 30. Okay, that's 5 times 6. So here's the matrix. So h10, h9, h21, h20. Okay, so if I sort of draw the coefficients of h again, so this is x to the 30. So what do we have? We have 21, and so I think before I had this was my 20, and this was my 10, and now we're dealing with 21 and 20 and 10 and 9. Okay, so there's 4 coefficients. They come in little groups of 2 because the genus is 2, and there's 2 groups because the genus is 2. And it's quite incredible that just knowing these coefficients lets you get these point counts over all extensions. I actually don't know the history of this result. I mean, it's very old. I think of it as folklore now, but I'm sure someone here would know who first wrote down this kind of formula. I think it goes back a long way. But if I now have this matrix, I can write down, for example, number of points over fp. I mean, I just get the baby trace formula here, so we wrote this down yesterday. h10 minus h20. This is mod p. And then if I want the number of points fp squared, I just get 1 minus, well, I'm not going to write it out. There's some ugly formula involving all these coefficients. It'll be the trace of this matrix squared. Right, so you can see you would have to do something like this times this and this times this and calculate the trace. One other comment I should make is the notation. I've put the f in the notation here because you could write down a different model for the curve. Right? You could do a transformation of x or something, and you'll get a different matrix. They're related in some way. But I like to put the f here to remind me it's this particular model that I'm writing down this matrix for. Any questions? No? All right. So now we've got this this trace formula. This is really great. So you can already see there's an algorithm coming out of this, which I'll get to in a minute, is if you just calculate these coefficients, then you can calculate the number of points by using this formula. And what a lot of the rest of the course is about is how do I calculate just these coefficients more efficiently than just multiplying out the polynomial, right? There's better ways of doing it, and that's really what the rest of the course is about. But before I go on to that, I want to talk about consequences of the trace formula for the L polynomial. And in fact, I learned a few things while I was preparing the notes for this part of the course. A few things I didn't realize, which is kind of interesting. So okay, let's write again n sub r, number of points over fp to the r. Now, so what do we know? We have this a sub f. Okay, this is a matrix over fp. And we know we can use the trace formula to compute these point counts modulo p, right? This is the trace formula. I wish I had a wider board here. My diagram is going to have to go around a corner in a second. That's okay. Let's see what happens. Now, okay, I've got these numbers n1 up to ng, and you remember that the L polynomial, if I know these guys as integers, then I know the L polynomial. So you might wonder, well, suppose I know these guys modulo p. Does that mean I know the L polynomial modulo p? Okay. Well, let's see how it would work. So first you take these numbers, and then you would try to compute the zeta function modulo p. I'll put question marks here. And when I say the zeta function modulo p, I guess I really mean just the first g coefficients, right? I mean the coefficients of t up to t to the g. Okay, now there's actually a bit of a problem here, because if you think about the formula for the zeta function in terms of these numbers, there are denominators, right? You have to remember, you have to write down, you know, there's n2 over 2 and n3 over 3. So that could be a problem when p is small. And then the other problem when you take the exponential, there's also denominators, right? So something funny could be going on. So I'll just leave the question marks there for a second, come back to that. Once you've got the zeta function, then there's no question that you can get the L polynomial. That's fine. This is okay. This is easy. Mod p. Okay, because if you think about, remember the formula is that the zeta function is L of t over 1 minus t, 1 minus, in our case, pt. So you just multiply through by this denominator, and that will tell you the coefficients of the L polynomial. So that's fine. This is the step that's a problem. Now, there's a few interesting things happen here. So first of all, this arrow, it does work if p is bigger than g. Now, let me just check my notes. Is bigger or bigger than or equal to? I think it's strictly bigger. So this arrow here is okay if p is bigger than g. And this is discussed in a problem. This is problem 4.3.3. And the reason is basically that these denominators are not divisible by p, so there's no problems. Okay, no surprises. But it turns out that this is not always, this arrow doesn't always work when p is less than or equal to g. Not okay if p is less than or equal to g. And there is a problem about that too. I had a lot of fun with these problems. And here's what I mean. This problem, 4.3.1, it shows you an example of two curves that have the same point counts modulo p, right? N1 up to, I think it's the genus is 3, I think, in that example. The point counts are the same modulo p, but the zeta function and the L polynomial are different modulo p. Okay, so what's happening is these numbers actually, modulo p, they don't have enough information to get the L polynomial modulo p, which is kind of annoying. Now, at some level, I don't really care because in this course, I'm mainly thinking of p being large, but it's good to be aware there's a little issue there. Okay. Okay, but, and here is the crazy thing, it turns out that there is a shortcut in this picture, is that you don't have to go via these little arrows. You can go directly from this matrix to this L polynomial modulo P, and in fact there is enough information in this matrix to recover the L polynomial modulo P. So you lose information when you go along this arrow. And let me write down what the statement is. And nevertheless, there's a beautiful theorem, 4.3.2, which says that the L polynomial is congruent to the inverse characteristic polynomial of this Hassovit matrix, I minus TAF modulo P. Okay, so that Hassovit matrix actually has the missing information. Now, that theorem, when P is bigger than G, you can prove it from this trace formula, right? You can sort of trace through what happens as you go through this diagram, and there's a problem about that in the notes, and that's pretty straightforward. When P is less than or equal to G, the proof is a bit more difficult, and it's not in this course, and I think I've got a reference to a paper of Manin that does it. It's a bit more involved, and I think that result might be due to Manin. Does anyone know? Or is it older? I don't know. Curious about the history of that. Okay, so what I'm going to do for the rest of the course is, just because this is so beautiful and simple, I'm just going to assume this, even though we don't quite know how to prove it when P is less than or equal to G in this course, but just makes life easier. So we're going to use this quite a bit. I should also mention that in section 8, when we go up to higher powers of P, I'm not quite sure what the analog of this is. I suspect there is a way to do something similar, but I don't know exactly what it is. And again, I haven't really thought about it much because I'm mainly interested in the case that P is large. But you can have a think about that if you're interested. Okay, what I want to do next is analyze the complexity of this algorithm that I've been hinting at. Okay, so the algorithm, let me quickly write down just briefly what is this algorithm, and we'll do a bit of complexity analysis. Okay, so this is what I call the expansion algorithm or expansion strategy. The expansion strategy for computing, I guess, the matrix AF and hence the L polynomial. Okay, so it's very simple. So the first step is we're going to expand out H is f to the p minus 1 over 2. We're just going to compute this polynomial. Okay, and we need to analyze the complexity of that step. And this gives us, of course, a sub f. We can just read off the coefficients. And 2 is to compute this inverse characteristic polynomial. So I want to spend a bit of time today talking about the complexity of these two steps, not so much for its own sake, but more just to give us some practice with thinking about these things before we do more with some other algorithms later on. Okay. Now, of course, there's lots of ways you could do these things, right? I'm not saying this is the best possible. I'm just going to give you one way of doing it, And so that we have a theorem that says what is the possible complexity. Maybe there's a better way to do it, or a different way to do it. That's fine too. So I should say just a few words about the computational model. And there's a little bit about this in section, I think 1.6 in my notes, only a little bit. So again, I just want to go back a few years to when I was first studying this stuff. I didn't realize for a very, very long time that there was such a thing as formal computational models. I was very naive, right? Now, of course, no one in this room is that naive, right? But I had no idea, and it was many years. I think it was a paper of who was it? Maybe Klaus Diem, I think, who wrote this paper about models of computation in computational number theory, and he was making the point that a lot of people never say what they mean, right? And how do you prove theorems about an algorithm if you don't say what the model is? And so I've tried to get on a bit of a campaign to always say what model I'm thinking about, and it's usually the multi-tape Turing model. That's the one that computer scientists seem to use as their standard model. And there are some disadvantages and advantages. I was discussing these with Drew the other day. But very briefly, it's a Turing machine, so a finite state machine. Has a finite number of states it can be in. And it has a bunch of tapes, a finite number of tapes. You have to decide in advance how many tapes you get. And each tape stores some data, potentially unlimited amount of data on the tape. There's no finite memory to this thing. It has not infinite memory, but potentially infinite memory, whatever that means. The point is that every step it can sort of look at where the current tape head is on all the tapes, and then decide what it's going to do. And what it can do is move to another state, and possibly write a value to each of the tapes, and slide the tapes over by one cell, whichever direction it likes. And then the complexity is the number of steps you take on this Turing machine. And so the one thing that might be unfamiliar in this model for people who are experienced programmers is you cannot access an element of an array in constant time. Right? If you want the millionth element of array, you have to walk over there. It takes you a million steps to get there, and then you can read it, and then you can come back to what you were doing. So that seems very restrictive, but it's actually not. It's actually quite a reasonable. It's actually much closer to your laptop than you think. Anyway, I don't want to spend all day talking about that, but this is the complexity model that I have in mind. Okay, so let's look at how to compute this power. So we're going to compute h f to the p minus 1 over 2 using a method called repeated squaring. Now, usually when people say repeated squaring, they're talking about a situation where every multiplication in your ring takes constant time. So, for example, if you're adding points on an elliptic curve, computing a large multiple of a point on an elliptic curve, each group operation